Yes, so this is my last presentation. So today you will have, for the final day of the workshop, you will have an overview of the libraries, so the math libraries, and then on the afternoon, so this will be in the morning. Then afternoon we will have some user experience, so which are very, very interesting. So the work was done to port some applications to the new Daint with the GPUs. So I will talk about this math library in Cray, so what we call Cray scientific libraries. So I will give you an overview how to use them for the CPU and how to use also for the GPU. Okay? So essentially, these are the libraries we are supporting, right? So they are the standard library, Cray Blast, so this is standard Blast optimized for Cray system, LAPACK, ScalaPack, these are inside the libc, what they call libc, okay? The libc is the math library from Cray for the CPU side. Then I will discuss about FFTW, standard FFTW, how to use it, very easy, there is a module for that. This is a way to do sparse matrix optimized for Cray, okay? And then libc for accelerators. This is I will call libc_hack, so libc_hack, essentially. I will show you results just because, of course, you can imagine that when you are running the same benchmarks on a Daint, so you will change the network, you will change the CPU, right? So you can have auto-tuning, you can get the best performance. So there is no real need to run all the benchmarks again on Daint, expecting completely different results. So I will show some results also for the whole system. So this is the XC system. So Rosa, let's say here. This is the TODI system, so where we have the GPU, and this is, of course, Daint. All right, so the idea behind to use the libraries, at the beginning was, yes, so we can have libraries, so we can reuse the code. So the idea was just for using the code. Now we use libraries just because we think they are optimized for a given system, so we want to just link to the library. So just to give an idea why we use them. And on a Cray system, this is even more true because what essentially you optimize for the given compilers that we have on the system, you optimize for a given MPI libraries, right, which is used on the system. So you can get the best from your system if you link to the library which are available on the system, okay? You don't download, let's say, FFTW and try to recompile it. You can get the same performance, but this just optimized by Cray, so you can just load the corresponding modules. So the idea behind is that you can get the best performance from those libraries with the minimum effort, okay? So the kind of things that you can expect is, first of all, we do some kind of node performance improvements. So we try to get the best. This is the case, for example, for BLAS. Okay? We try to get the best from the node, using, for example, shared memory, using the fact that we are running on a single node, and getting the best performance for a given CPU, let's say, for this case, for the Sandy Bridge. Or if you are using the GPU, of course, you can get the best from the GPU, from an NVIDIA card. Then, of course, we try to have the best performance from the network. So on the system, we have IRS network, so we try to get the benefit, the maximum benefit, so messages, all this kind of level or low-level mechanism for doing optimization and also adapting parallel algorithms to try to get the best from the network. So the code is basically, most of the code is based on auto-tuning. So what we essentially do is, so we have a set of benchmarks we use to train our code on a new system. So when we move to a given CPU to another CPU, we just rerun, let's say, auto-tuning, and we want so we extract a new set of kernels that we put in a new library, which is optimized for your system. Now, suppose we are in a case where we are using a specific function, which is not, for example, in auto-tuning, maybe you cannot expect the best performance, right? So what you just need to do is ask Cray to add the new function to do auto-tuning for this new function. Okay, suppose, BLAS, there are a lot of functions, right? So first thing you can imagine that we optimize for gem functions, but then there are others functions, okay? So maybe you want to get performance for other functions, and you can put this in auto-tuning framework, and you will then get the best when you are moving from one system to another. Okay, so this is an overview. So as I said, FFT, now we just support FFTW. Previously it was a Cray FFT. Now it does not support anymore. This is the standard FFTW optimized for the system. Then for the sparse matrix, you have Trulinos, PET-C. These two are, coming from this third library, okay, third-party library. Actually, I saw that there are no modules for that, okay? But then this is belonging to Cray. Also, this guy here is belonging to Cray. This is just a way to optimize for those libraries, okay? So I don't know if here at CSCS they have those libraries somewhere, okay? but essentially Cray is also providing support for those libraries. And then for dense algebra, you have BLAS, standard BLAS, LAPACK, SCALAPACK, and this is a way to mix precision from single and double precision, aspecting performance for double precision, okay? And this is used from the other libraries. So for using libc, it's quite easy. Usually when you are loading the program environment, the module is loaded by default. So we can do module list, right? And you will see that there is a module called Cray-libc. Okay, this is the libc module. So now with the wrappers, you will just need to this library, to this math library. So supposing your application you are using a BLAS function, and you have this module there, you will link to this BLAS inside the libc. Okay? For the GPU, so for libc-IAC, there is a specific module load libc-IAC. I know that for the next version, they will change, they will call again Cray-libc-IAC. Okay? But otherwise, at the moment, you can use this module here. For using libc-IAC, you need also to load the libc. So you are forced to load this libc and, of course, the GPU modules. For FFTW, you just do module load FFTW. For CASC, you don't need anything. It's already there. It's just implemented. And again, you just then use the wrappers for compiling. So you will just link them because we are loading the correct modules. There are good friends to use. So again, the modules, so you can get all the information you want. Or you can do module show libc. Let's say module show Cray-libc. You can get some information from there. Otherwise, there is this tool here. I saw that now this tool is not available anymore in the new version of the program environment, but I found that it's available in the old version of the program environment. I don't know if this is a bug or not. Anyway, with this tool, so you can run from here, doesn't matter. You just look, so if you run without anything here, we'll dump you this output here. It's tell you, okay, you can apply here an option, right, a library, and you can set from this library. So I want to just see what is available inside the libc. I will say, okay, this is the flag with the libc. It will tell me, okay, the current version is this guy here, and inside you have these versions of the libraries, okay? So you can do for the others. For example, if you do for Linux, it will tell you, okay, there is no module for Linux, so you cannot get anything there, but you can do for the FFTW and so on. So you will get an overview of what is available on the system, basically. Then clearly you can use the man pages. So there are man pages for intro libc and libc-IAC, where you can get links to the other man pages and so on. Okay? So I will put all the man pages that we can use at least to start to get information. Then from there you can have other man pages where you can get even more information. Sometimes maybe you are using different libraries, right? So you want to make sure when you are doing static linking that you are loading, well, you are using the correct function from the correct library, okay? So what you can do is to add the manus WL when you are doing linking, okay? So you specify which function, right? So in this way, manus by dgem underscore, okay? What it's telling you that when you are linking, it will tell you, okay, I'm taking this function here, dgem, from this library here. Just make sure, you see here, this is a libc cray underscore multiprocess, okay? There is also a serial version. If you go in this directory, you can see there are serial versions. So sometimes maybe you are sure for some reason, because you are, messing up with the environment and so on, you are sure that you're using the correct version of your function. Maybe it's not the case, okay? And maybe you will not expect any performance improvement in performance and so on. It can happen usually when you are using libc-IAC. Sometimes you think that you are using the GPU version, actually you are using the CPU version, and then you will get the same performance. This is just because maybe you forgot to load the module, okay? So you need to make sure that at least you can use this command to see what's going on. Of course, in case of dynamic linking, which is the case for the GPU, right? You can use the LDD on your executable, and will tell you, oh, right, so all the simples for gem are inside this library, okay? So you can see where it's taking the routines. OpenP is the default trading mechanism inside libc. So essentially, to have trading inside the libc, you can use standard OpenP num threads. But there are several cases that you need to take in mind. So if your application, there is no OpenP at all, then BLAS will use OpenP num threads. They will do trading for you, okay? So you call dgem, and dgem is using trading inside, just because your program is sequential. And then if you have a code with the trading, then if you are calling outside the parallel region, so outside the OpenP region, then you will call the parallel the multi-threaded BLAS. But if you are calling from inside a parallelism, just because you want to avoid nested parallelism, okay, libc would run without threading. Okay, this is clear situation, right? Unfortunately, the current version, this is a request was done here CSCS, by the way, so now it's implemented. The current version, suppose you are running, instead of using OpenP, you are using, I don't know, pthreads, some other mechanism to do threading. The library will not recognize that you are not using pthreads, you are using, let's say, you are not using parallelism. Even if you are inside a parallel region, because we are using pthreads, but this is not OpenP. So the library will not recognize that, they will start to run in parallel, and you will get some nested parallelism, which is not optimized. It's also true that for the current version of the library, 3.00, there is no possibility to change dynamically number of threads. So suppose you start with the 8 threads, then at some point I want to use 4, just because I want to use another function with 4 and doing something parallel, I don't know, task parallelism, something really strange. There is no way to change this. Just because libc will start, see how many threads we have from the beginning, and try to find it will create some buffers, and this buffer cannot change during the execution of your program. So there is no real way to change this. But this is we're going to change in the next release.
The reason for not having nested parallelism is because really you don't want nested, or it's because of race conditions?
Because, no, the race condition, it's over. There is no race condition. Because it's optimized, all those functions are optimized for a given environment, so they want to give you the same condition. Let me give you this example. Now they introduced some function to move data. And clearly, when you are moving data, you are bound to the memory bandwidth. So maybe you don't want, let's say you have 8 threads. Maybe you don't want to do those operations to use 8 threads, right? You have 3 ways to access to the memory. So using 3 threads, you will get a situation moving data where you have memory bandwidth limited. So they do, internally, they use, instead of 8, they found that it's best to use 4. So internally, they changed this number of threads. This is not because it's not, available for the user, but it's possible to do internally in the library. And now, yes, with the new version of the library, actually, I tested the new version, and it's possible to do these kind of things. All right, so let's start now to discuss about performance, right? So in the Cray BLAS, you have those libraries, Cray BLAS, sorry. In the libc, you have those libraries, BLAS, LAPACK, right? So for linear solver, eigensolvers, and scalapack. Those things here are basically, you want to get the best performance from the node, and those functions are basically based on a single function, right? More or less. They are based on gem. So you want to optimize this function. If you optimize this function from BLAS, then you can get good performance also in these other cases, okay? So we want to get the best from this function here. To do that, you need to consider that clearly, BLAS, gem means matrix multiplication, right? So you can have different matrix sizes. And usually, you can imagine that you have a case like you have square matrices. Every matrix has the same dimension. So this is a trivial case. And you can optimize for this case here. And then you can provide people to use this. But in reality, they like to use cases like this, where you have small m, right? So A, in this case, is small, or small n, right? Or this case is here. So if you need to optimize this library, you need to take into account all matrix dimensions, right? There is no real way to do a library where you are optimizing all possibilities, right? All gem possibilities, right? So how we do in Cray? Essentially, there is a framework to do this, and it's based on auto-tuning. So the idea behind is that you have, auto-generate several kernels, depending which different kind of optimization, can be cache blocking, can be a rolling, different kind of optimization. So you auto-generate all those kernels for the CPU and for the GPU. Then you will run it on the system, right? There is very long tuning on the system, and they will pick the best from the execution and put in a library. Actually, it's auto-tuning, so it will do several steps of iterations. It will find that maybe doing this kind of rolling is good, and they will try to figure out if it can do better at rolling, or bad cache blocking and so on. So up to the end, given kind of performance, you try to find the best peak performance. This is for a given set of matrix dimensions, not for all matrix dimensions, right? At the end of the day, you will get a library where you can get good performance, right? Usually, if you optimize for a given set of dimensions, then you can expect also for all dimensions usually, unless you are using really, really strange dimensions, right? So you can expect from this library the best performance on the node.
Doesn't matter which kind of CPU or GPU you have, right? You will just auto-tuning. So the next version of the library will be optimized for the new GPU or the new CPU. So this is an example. So what we do then is a comparison between our library and what is available. Let's say for the CPU, Sandy Bridge is MKL from Intel, right? So we try to do the comparison and we try to get at least the same performance, even better, right? No less than, this is the point, right? So we do this, you see here the line, so the green line is the libc, one thread, so this is just single thread execution, and then we have the MKL, and we try, this is the matrix dimensions, square matrices, but again, we do also for other dimensions, and you see that at least in some cases, most of the cases we are better than MKL, okay? So we try to find the best kernels, the best performance from the node. This was for medium square matrices. This is for large square matrices. And again, you can see that we are trying to get the best performance here. Okay? So this is just a way to optimize. Clearly, if you are, if you are in a case where I want to have the best gen functions for those dimensions. Maybe they are not already optimized with the auto-tuning. So what you can do is submit a request saying, okay, I want to get this best optimized function. So they will add in auto-tuning, and the code will auto-generate. So it will try different again, solution optimization and so on. Perché l'avevamo sostituito.
Che se non si buttano via.
Ma infatti, o forse sarebbero meglio quella ricaricabili, così ricordo.
Io non sono abbastanza potenti, questa cosa fa consumo, l'ira di mio.
Non ho lo stesso problema. Lo stesso problema, ho dovuto comprare la versione Termi, no Termi, si chiama induzione. Perché praticamente o li lasci sempre sopra, oppure basta si caricano un poco.
E adesso queste qui dovrebbero essere nuove. Il problema è che adesso l'audio magari è sparamane.
So questions so far? Are you interested to use this library? This first initial question, because if you are not interested, then there is no reason to discuss. Anyway, so yes. Essentially, yes. So you can imagine that this auto-tuning technique is quite slow, right? So you can expect the new version of the library for the optimized version, right? So, but we try to, for requests from customers, right? So that you can have the new version of the library with new dimensions and so on, right? Again, this is just because those functions are used then in other libraries, so we want to get the best performance from there. Now, for LAPAC, so I want to now do linear algebra inside a single node. Clearly, we are using BLAS under the hood. So if you are getting good performance from BLAS, then clearly you will have also LAPAC. And of course, you can use also multi-threading. So there is no, well, nothing to say that, right? So you can say man page intro LAPAC. All the man pages are like intro underscore something, right? And you can see which functions are supported, which kind of optimization, and so on. So also in this case, we try to do some special optimization by Cray because we are maybe in a node, so you want to get the best performance. But otherwise, it's just using BLAS at the end. ScalaPack is more or less the same. Still, it's using BLAS inside the node, but here we do also special optimization because of the network. So suppose now you are using ScalaPack, of course, in our system. You can also gain performance using asynchronous communication, so gaining performance just because of the network. So it's specifically for Cray system. Also, in this case, you can use intro ScalaPack. And then there is this technique I will describe here, which is a way to mix single precision and double precision. Clearly, when you are doing single precision in AVX now, you have 8 slots, right? So you can do, let's say, 8 times faster. But maybe I want to have the precision of double precision. So this is a way that you can mix between single and double, expecting the precision of double precision at the end. So you can gain a lot of performance. Ideally, you can gain a factor 2, but then at the end, you can expect between 1.2 and 1.7 because just it's trying to, adjust the precision to give you the double precision at the end. So you can gain a lot of performance if you're using this technique. Essentially, there are two ways to use that. So the first way, which is called the benchmark interface, essentially you just use the standard function from ScalaPack and LAPack. You don't do anything else. Then you set this, export this variable. So now, since we are exporting this variable, you will use in ScalaPack and LAPack this mixer technique RT, okay? And of course, you can expect some benefit. The other way is that expert interface. You can go here and see all the options. And usually, it will give you some functions, so you can replace. Now, you need to change the code. And it's not just setting an environment variable. You need to replace the code. Essentially, you can replace the ScalaPack functions, LAPack ScalaPack functions, with something like this, which is essentially you have RT, then you have given factorization LU, QR, and so on. Then the given method, factorization method, given data, so you can real complex, and then the precision for the mode that you are using, parallel or serial. So now you replace those functions. Why I want to do that? Just because maybe I don't want to change all my functions in my program to use this mixer precision. I just want to change for some of them, so I can replace them. And then you can get also feedback, so to see if it's converging, if you are getting good numbers, good results, and so on. Clearly, it depends on your algorithm. If you are bound to precision, maybe you don't want to use those techniques. But you can expect a lot of benefit, and this is the case, for example, for this example, for this function. And here is the matrix dimension, and you see that there is a benefit of 1.7x. And this is still giving you some meaningful numbers, okay? So you don't destroy your algorithm, your precision, essentially. And you gain a lot. For example, I can use this technique for bootstrap, for example, so that I can have fast execution, I can get some int, and then I can run my program just using double precision then, everything double precision. So it's a nice technique out of the box that I can use to gain something and to have a fast int on performance, okay? So 1.7 is something that we can expect. Again, it depends on dimension, it depends on precision, and so on. Questions? This is for all libraries, ScalaPack and LAPack, no single thread. Distributed, not distributed. Multi-threaded, whatever. And you are saying this guy here, oops. This case here, no, oops. No, this is not. It's saying 2 threads. But it doesn't matter the number of threads, okay? It will work in any situation. Internally, not really. So what I know is that they try to apply, starting for single precision, and then they use, for example, for reductions, for other, rounding, they just change to double. At some point, they have a threshold. They set from the final result if you are using everything in double precision, and if you are using everything in single precision. And they try to get the best mixture between single and double, depending on a given threshold. Yes, the algorithm will change. Yes. Yes. You can try it. Yes, here is the case with the LAPack, of course. Right. Now, yes, there was this question, yes, so 2 days ago. libc is available with GNU, Cray, and Intel compilers, okay? So I did this test just to make sure that I'm saying something true. What I did was I can do module show of the system of this Cray libc, okay? And I have a variable like this. And this is for Cray. But then if I load the program environment from Intel, I will have the same thing with Intel. If I do for GNU, I will have the same thing with GNU. And of course, if I go in this directory, which is the best, because then I can see, without loading all these program environments, I can see that there are also versions for different CPUs. For example, Sandy bridges, EV bridge, AMD systems, and so on, okay? This, again, just because we provide those libraries optimized for all systems we have. So you can do this trick, make sure that you are using libc, and clearly you can use also in Intel, when you are using Intel, replacing mkl, which is easy, because mkl is used if you're adding the flag minus mkl. If you're not doing that, then the developers will look at the libc and will try to link to libc. Now, FFTW, as I said, nothing to say except that you need to load this module, which is not loaded by default, okay? You need to load the model, then you can standard use the FFT. So you have kind of optimization where you can use the Windows file, And then you have the main page that you can use to get more information about FFT. FFT we are using is basically optimized for Sandy Bridge. So as I say again, you don't need to recompile your FFT and use it. You can just module code FFTW. So again, this is for sparse algebra. So it's a way to do also in this case tuning of special kernels for sparse algebra. And these kernels then are used from other libraries for sparse algebra, PETC and Trilinos, okay? So you can do also, if you're interested, instead of dense algebra, you do sparse algebra. And also in those cases, since maybe you are using one of those libraries, out of the box you will get performance from auto-tuning just because you're optimizing for these kind of problems. This is just out of the box. But again, as I said, I saw that those libraries are not available on Daint. There is no module load of those libraries. But suppose they are there, then provided by Cray, then you will use this kind of optimization from Cask. Okay? And yes, these are comparison where again we try to compare what is standard available, okay, and clearly what is optimized by Cray. You will see that usually this is execution time, so lower is better. You see that you are better than the standard library, just because we are doing this kind of auto-tuning. And the is again for Trilinos, same thing. Now we are talking about megaflops, so higher is better, and you see that it's much, much better. Okay? These are if you're interested in sparse algebra. Now let's move to the, let's say, the second big topic of the presentation, questions so far. This was everything related to GPU, but now you will see, CPU, sorry. Now you will see how it's very easy to move to use, let's say, libc for the GPU. Okay, this is the second topic. So let's stay with the CPU questions. Usually peak performance. Yeah. So now they are optimizing also, because one of the problems was that small matrix was not supported. Usually more than 16 times 16 you can have peak performance, which is between 15 and 16 gigaflops, right? So now, yes, they have also a version, new version of the library, which is also optimized with which is 12.2. So on the system now you have 12.1.3. The new version will be 12.2, which will be available next week. I think will be installed then. And it's also optimized for small matrix multiplications. The current version 12.1.3. You just do module available cray underscore libc, dash libc, you can see. Internally, there are environment variables. You can use main page. And there is a way also, if you don't want to use auto-tuning. So because auto-tuning, you will do also a runtime. You will do also a check on your input, and you will try to fetch the best kernel, right? So you will do these things at runtime. So if you don't want to do these kind of things, suppose maybe you are not interested, there is an environment variable that you can set, cray underscore libc underscore auto-tuning, and you can put off 1, and you would avoid auto-tuning. You can also set to avoid threading, for example. There is another environment variable, cray underscore libc underscore auto-threading, and you can put off, and you will just using environment variable. And you can set, in all cases, don't use auto-threading. So there are a lot of environment variables, just look in the main page. Then it will use, no. In this case, if you're using just the MPI, you need to set openp num threads equal 1. Otherwise, the system will understand that you are running in a situation where there is just one thread available, right? Will not try to conflict with the others, okay? But this is when you are running AP run. Nothing special there. But just to make sure, I will set the openp num threads equal 1. But again, this is something AP run will do for you. Right, so, other questions? All right. If you have later, then I will be here up to 4, so then I need to leave for a meeting. But just send me an email in case. All right, so libc. So this is something that you want to use, for example, to do your computation on the GPU. So the idea behind is that you have all those functions from BLAST, LAPACK, and SCALAPACK optimized to run on the GPU. The idea behind this is that essentially you don't want to change your code. You just want to load a new module. Okay, I will show you, which is the libc hack module. And then you want to rerun your code. And the system will say, OK, maybe this gem function can be executed on the GPU. It will move for you, not touching the code, it will move for you the execution on the GPU. Of course, moving data and so on. Okay? So it is fully compatible with OpenMCC, but you're not forced to use OpenMCC. You can use CUDA. Okay? You can use any technique you like for the GPU programming. And then, of course, you can use libc hack. So again, it's just a way to write functions. So the idea was that we want to use the standard. So we don't want to add a new interface to functions. And just to tell you, OK, again, you can use the main page. Here, the thing is that libc hack is available for Cray and GNU. It's not Intel. And essentially, the reason that there is in Intel no easy way to use the CUDA function. Under the hood, this function is use CUDA. Okay? So this is one of the reasons. So we just support Cray and GNU, okay? Now, there are several other libraries that can do the same thing, right? So you have QBLAS, let's say. But the point is that QBLAS is not standard, right? So it's, the dgem is QBLAS dgem. So suppose you have your program, which is running on the CPU, and I want to just move the execution to the GPU. All right, easy, right? So I will open my program and change all my function using QBLAS. The problem is that maybe you don't have QBLAS, in this case, dgem in Fortran, for example, right? So it's going to be a mess. So the idea behind this is that you can have the same interface in Fortran, in C, and C++, and basically you will not change from moving from CPU code to GPU code. So it's just loading a module, okay? So, and then, of course, we do auto-tuning also in this case, and we try to beat these people here, or all the others, okay? If you are finding a function which is fast in a given library, let's say Magma, just tell us, then we'll try to optimize, and we'll always win, okay? Don't try this. But anyway, so the idea is, of course, to get performance. So how it works? Essentially, there are three interfaces. So I have my code. This is, oops, sorry. This is the standard code, right? Writing standard library for standard call, sorry. So I'm doing this. Then the library will tell, OK, I'm loading the module for libc hack. Will tell, OK, is this A large enough that it can be executed on the GPU? Of course, if this operation is very, very fast, then there is no real need to use the GPU. Because the time that we are spending to move data and to start making the evaluation on the GPU, it's not worth, right? Because you can do the same thing on the CPU. Then it will start to say, OK, where is A? A is on the GPU, on the CPU. Clearly, if you have already A on the GPU, then you will do the evaluation on the GPU. Fine. So if A is a pointer, let's say in C way, it's a pointer to a GPU part of memory, then the execution will be on the GPU. But if it's something on the CPU, then it will be executed on the CPU. But then it depends on the dimensions. If I say the dimension is large enough, then it can make sense to move the data to the GPU and do the evaluation on the GPU. So again, it's not changing the code. It's just doing this kind of a compiling time. A compiling time will understand if this function will be replaced for you to a GPU call, right? So depending if A is small or if A is on the CPU, then I will do this evaluation on the CPU only. But if this function is slow enough on the CPU and it's good to move to the GPU, then I will do the evaluation on the GPU plus the CPU, or just the GPU, if you like. So you need to change the code. Just load the new module, recompile, and it will do this evaluation for you. This is the first interface. Yes? Yes, I will show you later. Yes, yes. If it is on the GPU, OK, fine, we'll do on the GPU. It's clear the data are already there. If it is on the GPU, you will try if it is useful to move the evaluation on the GPU, based on the fact that you are, trying to figure out how many flops. It depends on the operations, right? It clearly will do that. And again, it will do also the hybrid evaluation. It can do also CPU, so doing multi-threading on the CPU plus the GPU. So out of the box, you can gain a lot of performance. The other way around is that now you have a device pointer. See here, D_A. So this is something that is already on the GPU. Here, there is no choice. You will do just on the GPU. Okay? This is the simple interface. So not touching the code, I'm just doing that. And maybe I want to force the system to do the evaluation on the GPU. So what I can do is add underscore ACC. Here now I need to change the code. And this function here no matters. Then I need to submit a GPU pointer because I need to tell this function, yes, this is a GPU and do everything on the GPU. Okay? So there is no need to check now. And of course, if you know that this is faster on the GPU, then there is no need to check the dimensions. Okay? This is dynamic, right? Again, it's a runtime. So at runtime, depending if you're changing M or N, you have a switch, and you need to figure out if it's good to run on the GPU or not. And then if you want to do the data and so on. Clearly, there are also cases, further interface, where you want to force to use on the CPU. Now you can set underscore CPU. I will explain why maybe you want to have this on the CPU instead to use the heuristics case, right? Try to figure out. It's best to run on the CPU or on the GPU, okay? Maybe because you want to have, you don't want to use the GPU memory because you are doing other evaluations, so on. So maybe you want to just have it on the CPU side. It's just because we have several of those functions, so I want to just to see what is running on the GPU, want to decide what is running on the GPU, what is running on the CPU. So the simple interface basically it's just try to figure out it's good or not to run on the CPU or GPU. Yes.
And then if you say underscore ACC, so then you know it's on GPU. Then the question is, if you have multiple of this, imagine you have a for loop of this thing. So is it all the same stream, or will
it will? No, it will try. No. It will try to optimize it. Yes. Yeah. If you look at the main page, it's basically an asynchronous. Yeah, there are flags for that. So there are functions where you can set asynchronous here. And yes, then it will use streams, filling all the available streams. So in this case, again, it depends also where the data are, right? So if the problem is too small, then it will do also the operation on the CPU. It's clear, right? But still, you need to change your code. So what you have is +1 and +2. Since they are not computational bound, then you will just run on the host. Okay, so you can expect that it will change here if the computation is large enough that it's worth to run on the GPU. And again, it's a way to know. Yes, there are flags, verbosity that you can dump what's doing, where it's doing, and so on. This is an overview. Okay, go in the main page, you will get the other informations, and then you can expect even other improvements because the library is actually evolving. The device interface, again, you just need to change your code now, so you can put underscore ACC. Well, it's nothing really, and then, well, it's not completely changing. Maybe you want to do for some functions. And then, yes, you need to copy the data, otherwise it will give you an error, okay? It will tell you, this data is not already in the GPU, so I can do this evaluation. Now, the third case is when we are using just the CPU. Again, can be, for example, I don't want to use the GPU memory because I'm doing other evaluations. Maybe it's not enough, the GPU and some memory and so on. Or maybe I have some kind of organization on the CPU. So I just want to make sure that this function will run on the CPU only. So I can put underscore CPU, don't change anything. And of course, it will run on the CPU side. So how to use it? First of all, you need to load Cray and -libc. This is done by default when you're loading in the program environment, okay? And again, this depends on which kind of program environment you have, Cray, GNU, or Intel. Then you do module load libc underscore ACC. This is not loaded by default. You have 4 tendency interfaces, so it's a basic column measure. So basically, you don't need to, change from C to 4 tendency. It's basically the same. Clearly, since we are using a GPU, we need to load also the module to use the GPU. Right? So Cray P-Acel NVIDIA 35, which is for the Kepler. And then you use compiler as usual, using the wrappers. Since you are using GPU, it will be a dynamic library, a dynamic executable. Then clearly, since you are also running on the CPU, right, you can run on the CPU and GPU or both simultaneously. You can set the OpenPNUM threads as usual. And you will get also threading on the CPU side. And clearly, if you're running multiple MPI ranks accessing to the same GPU, you need to set the Cray CUDA MPS. Otherwise, remember, right? Only one process can access the GPU. So you need to do this kind of multiplexing and setting this variable. And then clearly you can execute your code as usual. Yes, then there are binary variables to understand what's going on. Otherwise, you can use Cray path and will tell you this function at this line is executing on the GPU. Or is executing 80% on the GPU, 20% on the CPU. So let's take this example. Easy dgem. So without touching anything, I'm just loading the module libc_acc. So the system at runtime will say, OK, seems that these dimensions of those libraries and the position of those libraries are good, so I will move the evaluation on the GPU. Okay? Or I can do the hybrid evaluation, GPU and CPU. Okay? This is out of the box. Clearly, it will copy, if it is good to do on the GPU, it will copy also the data for you. So no need to change anything, no need to add anything else. Okay? It will do for you. But now, you can also interact with OpenSCC, if you like. Okay? We are using the Cray compiler to move data. Otherwise, again, you can use CUDA. It doesn't matter. You don't need to use OpenSCC. OpenSCC is much easier to move, to allocate data, and so on. Indeed, what you can do now is, OK, I just want to run this function now on the GPU. So first, again, since we are using this function, first I need to move the data on the GPU, remember, right? So I do this pragma directive, ACC data copy, A, B, and C. I will copy on the GPU. Then I start this region, parallel region, doing something, let's say. Then I start a given portion of the code. I say, OK, now give me the pointers, the GPU pointers. I just want to use these GPU pointers in this CPU call. Again, this is a CPU call, right? It's not inside the parallel region. It's outside the parallel region. Okay? And now those pointers, A, B, and C, are the GPU pointers. So this call here is saying is a GPU call. It's taking GPU pointers, and it will run on the GPU. Adding few directives, I mean, I can remove those. I just need to add this directive for the copy. I just need to add this to get the pointers from GPU. And then again, I can say, OK, now copy back the data, and then end of the data. So we'll destroy the data we'll free the data on the GPU. Okay? So this is, if you remember from 2 days ago, how it works OpenSCC, you can see that it's very easy. The thing is now I'm saying, OK, this is the GPU call, and I'm using GPU pointers. And we'll do this on the GPU, only the GPU, clearly. But libc_arc is smart. So what does it work? Yes, it's smart. So you just say, wow, these are GPU pointers, right? So why I need to change the code saying that I need to run on the GPU? The tool should understand that these are GPU pointers, so I just want to run on the GPU, right? So I can remove here _ACC, because again, I'm using GPU pointers. So there is no need to say just use the GPU. Okay? The data are already on the GPU because I did this trick and so on. Okay? So at the end of the day, to use this library in your call, you just need to copy the data and then use inside your call the data, the pointers to the GPU. Again, these are similar for Fortran and C. They have interface, specific interface for C, so no need to put & all the time. It will just change to pointers. Okay? It's nice because it's not linking to Fortran. There is a C interface, it's like C++. So just dgem is enough. Questions? I mean, suppose you have your program. What I will do is module load libc_acc and rerun. That's it. And then I can see what is moving to the GPU and where I'm spending time. Now, suppose I have several of these calls on the same data. It can be the case. Maybe each of these calls will move data back to the CPU. GPU, CPU, CPU, GPU, and so on. So maybe I want to use these OpenSCC regions or CUDA regions to keep the data on the GPU, right? I don't think so. I don't think so. I'm serious, I'm not sure, but I don't think this can be done. So you want to call this function from a CUDA kernel?
Yeah, for example.
I don't think this is possible. This is, again, inside the CPU code, so this, I think think. But anyway, so other questions? Anything. Anything. Good point. Okay, if you do a main page, you see that there are some functions which are like BLAS, right, directly implemented for the GPU. Some other function like LAPACK or ScalaPack, not all functions are implemented for GPU, or under the hood, they use GPU calls, BLAS calls. The point is, does the library using, like, let's say, GPU to GPU communication? So does LAPACK, ScalaPack, and understanding that everything is running on the GPU, so can do everything, so high level? Yes, this will be implemented in the next version of the library. Actually, was requested by CSCS. So the current version is try to get the best. It is not really optimized when we are running in distributed systems. So the major, the main function was optimized is gem, basically. But yes, they are trying to optimize. So if you have a function and you think that you want to gain, you want to have better performance for this function, just let us know. And we'll try to implement it for the next version. It's all the time, how to improve those functions. So clearly, there are ways to improve performance, based on there are advanced controls. So let's say, when you are running in a GPU, there is something that's called pinned memory. How many of you knows what is a pinned memory? Good. Know the others? Okay. Just to tell you, it's a way to allocate data on the GPU and the CPU and to gain the best bandwidth when you are moving data. So if you're doing those operations, let's say in a Scala, on a LAPACK, right, you need to do a lot of movement, right? So you need to figure out the best bandwidth when you're moving data from CPU to the GPU and back to the CPU, right? So to gain the best bandwidth, there is a way to allocate data, which is based on this pinned memory. So there are ways to allocate the memory to gain in bandwidth, let's say. So there are controls that you can use. Again, you can do the main page. I put just some of them. So for example, you can say using this function here, of course there are flags here, options. Using this function here, you can register a given buffer on the GPU so that you can allocate a given buffer to reuse this buffer for your libc functions. And then you really need to do allocation and the allocation are consuming a lot, okay? So it's to do buffers, even on the CPU, clearly, but on the GPU even more. So clearly, you want to keep this, and you want to reuse it. So there are ways to improve performance, to do allocation, and so on. Let's say there is also a way, which is maybe, in this case, you need to change your code. Actually, you need to add those functions. There is also a way to initialize the libc. By initialization, basically, and of course, you need to finalize at the end. By initialization, we'll create some buffers for you at the beginning, right? So then all functions behind the buffer will use these buffers, and we gain a performance by doing this, okay? So if you want to reach peak performance, you need also to take into account that, there is not shared memory. So you need to move data between CPU and GPU. Yes? Yes. This library is based on cuBLAS at the end. Yeah. So, yes, this is. Yeah. Gem is auto-tuning, auto-optimized. So we try to beat. No. It's not. Well, in some cases, it's using cuBLAS. In some other cases, you find that it's best to use our optimized version of Gem. Yes, so the thing is you need to take into account that this is not thread safe. So if you are calling those functions for multi-threaded and you are calling the GPU version, maybe you can have some problems, okay? This is trivial because we are using different streams, so we are using different optimization, so you can have some problems from here. There are also environment variables you want to set. So essentially, instead to put underscore CPU underscore ACC, you want to force a runtime to move everything on the CPU, everything on the GPU, right? Instead to open your code and changing and so on. So what you can do is set this environment variable. 0, which is the default, is basically automatic mode. as we described, right? So we try to figure out, okay, this is good to run on the GPU. This is good to run to keep on the CPU side. Otherwise, you can force to have everything on the GPU or everything on the CPU, just setting the environment variable. But then you can do even more. I just want to have one given function to run on the CPU, to keep on the CPU, or to run only on the GPU. So I can set libc, ACC, bypass, and then I can set the name of the function. Let's say I can have sgem, for example, here, and put the usual numbers, 0, 1, 2. For just the gem function, I have also this option 3, which is an optimized way, so to answer to you, this is an optimized gem for the GPU. So if you don't use the optimized, they will use QBLAS. Still, again, it's based on auto-tuning. So if you are not better than BLAS, we try to beat BLAS, QBLAS, sorry, okay? And again, there is also a possibility to use this in Scala pack, right? So now you are running in multiple nodes. As far as I know, this is the only library. Are there any other library to do Scala pack with GPU? Okay. This is just to make sure, because NVIDIA is providing you a way to do in a single node. So LAPAC with GPUs, QBLAS, and then I think they will come with that. But at the moment, this is the only library that is capable. Which one? This is something that we can. Yeah. Yes, yeah. So as far as I know, yes, again, this is the only library, and now we are optimized because they were requested by CSCS. So clearly, I can explain to you the case. Suppose now I'm running PDGem, right? PBLAS, right? So on different nodes, which means that now I have to move data around the nodes and then move the data to the GPU, right? So what you can think is that they will do the composition over the nodes, and then inside a node, so you will use the standard PBLAS, doing making communication around the node, and then you will use the GPU version inside the node to make the portion of multiplication inside the node. And then, so you need to move back the data to the CPU, then back to the GPU, and so on, and so on, and so on. So essentially, maybe you don't want to use the communication between CPU and GPU, just to want to avoid this kind of communication. So in the meantime, you are doing communication over nodes, so you can do evaluation on the GPU. For doing this, you can use GPU to GPU communication, and this will be implemented in the next version of the library. So the only thing you need to do, if you are in these cases, is to set the GPU to GPU communication environment variable. So you just set this environment variable equal 1, and then you will use a Scala pack version, a PBLAS version, optimized for GPU to GPU communication. So it's similar to say that I'm running just on the GPU, and even the communication will be done between GPUs. And you can gain a lot. Actually, we found that at least you gain a factor 2 just doing this. So if you're using PDGem, you can gain a factor 2. This will be implemented. And then, of course, there are requests for other functions that will be also included. And yes, this is clear. If you are running in this situation, so when you are putting the GPU in place, you can see that there is large performance. And then, of course, you can also run in a situation, this is gigaflops, right? So you can run from CPU, right, to CPU plus hybrid case, and then you can run also just the GPU. In this case, it's slower. I think this is a mistake here. It should be the other way around. Anyway, the hybrid mode should be faster, okay? I think here it's just because it's moving data, maybe. Okay, I'm not sure about this plot. So, but again, you know, when you are moving to the GPU, of course, you can have speed up from the GPU. Same thing now with a given different function, and now we are comparing single node performance, so we are making comparison with Magma, and again, you can see that libc hack is faster than all the others. Clearly, it's much faster than the CPU, okay? So again, in this case, I'm calling this function. I'm not doing anything else. I'm not changing the code, I'm just loading a new module. You see that's really fast, okay? If I'm using Magma, I need to replace this function with the Magma function. Okay, so you can imagine that it's really, really fast. Another function, again, you see that our library is faster. All these kind of things, of course, are just things if you find, again, that magma is fast in a given function, or plasma, whatever you want there, just let us know, and we will work out to improve it, this function, okay? So in summary, we are half an hour early. Anyway, in summary, essentially, you can expect from libc the best performance if you're running clearly for the Cray system, because are optimized with auto-tuning and so on for the Cray system. You don't need to do anything. You just need to load the modules, recompile, and they will link to the version of the library, okay? So this is something that depends on your program environment, and then you need to use the wrappers to run this. You can use threading on the CPU, just setting the OpenPNAM threads, okay? And you will get threading also on the CPU. And then, of course, this is the libc underscore ACC, libc hack, which is give you a possibility to use the GPU without touching the code, so minimal effort, and you can use you can have your execution on the GPU. You can have also the hybrid case running CPU and GPU, and you can have some kind of control and to gain performance running on the GPU. Okay? Again, the new version of this library will have new implemented functions with the possibility to have better performance. And this is we are moving now in a situation where we want to use clearly not perform for a single node, but we want to use best performance also for distributed functions. So P blast and Scalapack. And again, I say the major optimization is using GPU to GPU communication. Questions? Then what you can do is try this module, and if you have your application, favorite application, and see what's going on. And yes, look at the main pages. There are some verbosity flags that can tell you what's going on. And clearly, you can run CrayPath, and will tell you this function is running on the GPU, is taking this number of flops, is moving this number of data, this amount of data, and so on. And see if you can gain. That's it.
What about acceleration performance for the FFT?
FFT at the moment is coming from FFTW, right? So I'm not aware of any kind of, because unless you do a specific library, you should ask again to this other person. Is there any FFT for GPU? Clearly there is cuFFT, okay? This is not to say, I'm thinking in terms of distributed and parallel. It will be really complex then, because FFT is moving a lot of data. So I'm not sure that you can gain a lot. Well, you can do your decomposition, let's say. There are.
Therefore, my question, because then you have to move a lot of data.
Yes, it's really complex to gain performance. I can tell you Quantum Espresso, let's say, is doing this kind of things, but it's node by node. It's not doing these things moving, in a parallel situation. So it's still using serial. I think that we use cuFFT. Yeah, I was thinking in terms of general library. Yes, sure.
We go back to slide number 29. Sorry, I missed this part of the discussion.
Yeah, sure. No problem.
Okay. So when you say several scientific library packages are already there, what do you mean?
No, inside this library. Already there. Sure, already there. Yeah, sure. Not to say that they are included. Yeah. Already there to say that, of course, we are not doing yet another library. We are just doing something to improve the situation. And, of course, we want to get the same performance of these other guys.
We have to be a little bit careful of what we claim because, for example, Magma and cuBLAS or cuFFT, Sparse, and so forth, they are already available on Daint. Kula and Sparse, I know, isn't yet available because it's proprietary.
Yeah. Yes. This is just to say that, yes, there are other libraries. Yeah. Several scientific, yeah, I think I need to put other instead of several, yeah.
So Kula is essentially a subset of LA-Pac.
Yes.
Right? So maybe that was what you were referring to. It doesn't come from NVIDIA. It comes from another company. But essentially, it's a subset of
Kula does not come from NVIDIA.
No, it's quite expensive, actually.
Yeah, I knew it was NVIDIA, but I thought it was from NVIDIA.
No. NVIDIA does good job if something open source, right? Then they can include it easily. But this kind of things is not the case because it's a really complex situation. Yeah. This is marketing stuff, right?
No, I mean, if there's enough interest, if the user community demands it, then you
Yeah.
make a case for that, you install it.
But I don't even know what the performance is. I just know it's there. But
It's favorable when compared to Magma, either a little bit better or a little bit worse. But Magma is available, and Magma is free. Right?
yeah, no, I know.
But no, they've done good work, and it does perform.
So by the way, this afternoon we'll have this meeting at 4, and actually the meeting is for this discussion about new improvements in libcAC. So the discussion is ongoing. So if you want to, contribute or whatever, you want to collaborate, just send me, or maybe Will is the best contact person for that, for CSCS. So the next libcAC will include some improvements. It's version 3.0.1. The moment is 0.0.0. So not major improvements, but still there's something there new, okay? And then yes, they will change the name and they will move to version 3.1. Okay, I basically completed my presentation, so